Very good. Yeah. Here. Very good.
Broadcasting live from my kitchen in Urbana, Illinois. It's Astronomy on Tap number 7. Welcome, everybody. My name is Patrick, and I am a third-year graduate student with the Department of Astronomy, and I will be your gracious host this evening. I hope you all have a beverage of choice as we sit back, relax, and learn a bit more about the way our universe works. Personally, I am delighting in a raspberry wheat ale from our friends of the show at Blind Pig Brewery. Not sponsored, but please sponsor us. And before we begin, I just want to remind everybody that this is an interactive event, so please feel free to use the YouTube chat bar. I will be monitoring the chat as the show progresses, and if there's a question in the middle, I will stop our speaker and we at the appropriate time and ask that question, or you can hold your questions to the end. We will answer any and all questions all the same. Tonight, our speaker is Professor Helvi Witek, and she is a part of the Department of Physics at the University of Illinois at Urbana-Champaign. She joined in January of 2020 as an assistant professor after obtaining her PhD at the University of Lisbon in Portugal, with postdoc positions at the Universities of Cambridge and Nottingham in the UK, and was a recipient of the Marie-Curie Fellowship at the University of Barcelona in Spain, and a Royal Society University Research Fellowship in London, also in the UK. Tonight's talk is titled Whispers of the Dark Universe, where we will hear about gravitational waves, the sounds of the dark universe, where they come from, how we use them to explore long-standing mysteries of our universe. So without further ado, please take it away, Professor Witek.
Okay, good evening, everyone. It's a great pleasure to have you listening in to an evening program on Whispers of the Dark Universe. Before I go ahead, let me just thank Chris and Patrick and Kale for making this event possible, for moving forward with Astronomy on Tap, even though we are all going online. Unfortunately, I don't have a nice beer with me right now because I just had an operation this morning, but I hope you're all going to be fine and you enjoy the evening that we will have together. Before I start, just a little warning, there will be sounds in this presentation. So don't be alarmed and make sure you have your mics on. Okay, so let's just get started with the first sound, the first whisper of the dark universe. What you just heard was a soundification of a gravitational wave that was emitted by two black holes that had a mass 30 times as massive as our sun each, that collided and emitted an energy that was equivalent of 3 suns. That signal was emitted about 1.4 billion years ago, when here on Earth, just the first single cell organisms developed, and we have detected this signal back in 2015 for the very first time. So that was the very first gravitational wave event that really opened our senses, our ears, to learn about the universe in a completely different fashion. Now, I've used a lot of jargon in my first 2 sentences. So tonight I want to take you on a journey where we pass by these concepts of space-time, ripples in space-time, black holes, and gravitational waves. So let's start slowly. What is space-time? Well, in the simplest terms, just think about it as putting space, so the 3 spatial directions, whether you're moving forward or sideways or up and down, together with time. Like we are all aging, we are all moving forward in time, whether we want to or not, but that's our direction of time, and taking those together gives us an idea of space-time. Scientists have a slightly more complicated version thereof, but for tonight, let's just think of that as space and time together into space-time. Now, the next concept is that space can actually be curved. And that's, Chris, where I will have my piece of paper and a pen. So if for a moment you can actually move that over. Exactly. So what do I mean by space is curved? So let me start with just a flat sheet of paper, and I will draw a line on here in a minute. So taking my pen, having two straight lines here. Now, if I curve my sheet of paper, if I try to make a ball out of it, you will hopefully see that these lines start approaching each other. Not because their direction changed, but because our space, in this case, our sheet of paper itself, curved. Now, if I'm to try and form a saddle out of this, then these lines will go further apart. If I try to make a sphere out of it, then those lines will get closer together. Now, that gives us an idea of how we can curve space. Okay, so Chris, we can go back to the slides, where I have that in a slightly more fancy fashion, but I thought it would be a little bit more interactive if I actually show you on a sheet of paper. Yeah, so we have flat space here, two lines just being parallel. If we try to draw those parallel lines on a ball or on a sphere, then those two lines would converge. Think of this as, say, the North Pole of Earth. You and your friends start here. One goes down to Chicago, the other one goes down to close to Berlin, where I'm actually from in Europe. And those parallel lines will diverge. Or if you have something like a saddle, then those two parallel lines, here they will converge, here they will diverge from each other. Okay, great. So now we have a concept of how space can be curved. Now let's take a next step and let's think about an analogy. Again, so I'm not, Chris, we are staying on the slides, but let's take some analogy to a space that we have. So how can we curve it? Well, we can curve it by putting a mass onto this. So think of an analogy where we have, say, a trampoline or a rubber band and would put a mass on that. So I have that as a picture here. And the ball that I put on my trampoline would be, for example, the sun. So I put a mass on my rubber band and we are deforming, we are curving space-time here. Now let's take a small ball that we make to look like the Earth and let's try to move it around the sun. Let's just give it a little kick. And instead of falling directly into the sun, it will follow the curved space here. So it will actually follow a trajectory and orbit around the sun. And that's what's actually happening between Earth and our sun, or other stars, other celestial objects. So instead of having this somewhat mysterious force of gravity, what we have here, and that was a great idea, that a great understanding that Einstein had back in 2015, that matter objects are curving our space-time, and that then other objects would follow that curvature. John Archibald Wheeler put that together in a very nice saying: space-time, remember we talked about this in the beginning, tells matter how to move, and matter itself tells space-time how to curve. So this little object here is also curving space-time, so there is some interaction here. Okay, so this was the first important concept for tonight to understand. Matter objects can curve space-time, and if we have a very massive object that's very compact, like for example the sun in comparison to the Earth, then the curvature of space-time is larger. Okay, so now I'm taking a big jump from what is curvature to asking the question, what is a black hole? And I guess, Patrick, this would be a first place for pause if there are any questions on the chat. I do not, oh, I'm not signed in, so I don't actually see them, but if there are any questions at this stage, we can take a short break.
There's actually no questions at this time, but I would like to ask a question. What makes a black hole black? Why is it called a black hole?
Okay, so that's exactly what we're going to talk about in the next few slides. So, but before I tell you what makes a black hole black, I will actually take another analogy with you. And what I will look at first is a drain. So if you, for example, take a safe drain, if you go into your bathtub and you let the water out in the very end, you see that the water would go down that drain. Okay, now if you want to play around a little bit, you can fold a little boat, and then you can, well, imagine you put a little motor onto your boat, and you try
Helvi, are you with us? I think you are frozen, at least on my end. I do not hear anything, so I will keep stalling as long as we need be. So I hope everybody is enjoying, as I said, the talk so far, and whatever beverage you have decided, alcoholic or non-alcoholic. Oh, it looks like maybe our insider Chris maybe can give us an update as to what is happening. Chris, if you were on the line, would you like to provide us with any update?
No updates. I think Helvi is just having some internet problems. She should hopefully be back in a couple of minutes. So sit tight and don't go far.
All right. Well, during our commercial break, we would like to bring to you, as I said, Blind Pig Brewery. This is a local brewery that has done very kind things for us and for all my Mug Club friends out there. Cheers to you. I know we're all waiting for the day where we can get together at the brewery itself and I just hang out and talk about life and enjoy some beer. And oh, it looks like that maybe we have established reconnection. So once you are ready, we will turn it back to you for the continuation of your presentation. Thank you everybody for sticking with us, and hopefully things go off without a hitch. So
yeah, okay. Yes, thanks, Patrick. So I apologize for disconnecting, losing my connection. As I said in the beginning, I have my phone next to me, so if that happens again, I'll connect to my data on the phone, and I typically need 1 or 2 minutes to reconnect to Zoom. So please bear with me. If that happens again, take the break to have your beer or glass of wine or whatever beverage you have. So I was talking about looking at bathtubs and drains, which I said, well, it's quite far away from a actual black hole. But what I was trying to say is the following: that if you are inside a certain region, then your boat, no matter how strong your motor on the boat is, will not be able to leave that region anymore, will not be able to get out of the drain, and will just fall into this high curvature region here. And there's one limiting surface where your boat, if you have a very strong engine, may not be able to escape, but it also just doesn't fall down the drain. And that surface we can call a horizon. Now, let's go away from that analogy. So I hope that gives you an idea of horizon and falling down the drain as a high curvature, because something very similar can be used to describe a black hole. In particular, if you replace your boat with light. So I don't have a laser pointer here because you wouldn't see it online, but if I were to shine with a laser pointer in one direction, then usually your laser lights are here. I have a picture of that. Usually your light would go straight, but if space is curved, as we saw and discussed in the very beginning, then actually that straight line is no longer a straight line. It follows a the curved space, so it will actually be deviated a little bit. So if you're in a region where the curvature is not very large, then you may start here and your light curve may end up somewhere here. So if you're sitting here, you observe light that actually comes from behind your object. If your curvature is a little bit larger, this deflection of light will be a little bit larger. And if you have a very compact and very massive object, then your light ray would follow these curves here, would not be able to escape that space-time curvature anymore. And that's when we start talking about a black hole. So in colloquial terms, a black hole describes an object where the curvature of space is so large that light cannot go away. So if you take this boat analogy, if I have my boat sitting here and would shine some laser light from that boat, the light would be deviated, would never reach anybody sitting out here. It would just go around our compact object here. Okay, so that's what a black hole is. Now, what happens if I fall into a black hole? And of course, one may think about a lot of drama in the very beginning, but let's take it step by step. And here I have an astronaut. Let's say she has a friend sitting over here and trying to get signals that she is sending from here. So let's say she is using some laser light, very strong and powerful laser, and trying to send information, sending light to her friend sitting somewhere over here. Now, if she is still very far away from the black hole, she will send the light, and then after a certain time, given by the speed of the light, her friend will get a signal. Now, as our astronaut gets closer and closer and closer to the black hole, the time that it takes the light to reach her friend will be longer and longer and longer. Now, as our astronaut gets to the black hole, falls for herself into the black hole, her friend will actually never see her fall the black hole. She will just see the light coming later and later and later. The astronaut herself will actually not necessarily feel very much as she starts falling into the black hole. Now, as curvature gets larger, as our space is more and more curved, the astronaut will get stretched. But usually at the horizon of a black hole, the curvature is not all that large yet. So she may not actually notice that. But as she falls into the black hole and gets closer to the curvature, closer to the high curvature region, she will get stretched and stretched and stretched more and more. And that's where all the drama happens, and it can potentially be painful and ultimately quite deadly. So I would still not recommend falling into a black hole if you can avoid it, but initially she will not actually feel all that much. Okay, so yes, good. So the next question we may ask is, how large is a black hole actually? And that goes back to the measure of how large the surface of no return is. So how large is the horizon? And that radius for the surface can be described by the mass of our object and then some constants. One is the Newton constant, the other one is the speed of light. Well, you don't have to look at the formula too much, but just to give you an idea, if I were to take our sun and could compress it and let it collapse into a black hole, its size would be 3 kilometers or some 1.8 miles. So if you wish, just the size between the downtown Urbana and downtown Champaign. Now, if I were to take our Earth, all of our Earth, and compress it together, overcome all the pressure that resists collapse. So if I were able to compress our Earth into a black hole, then it would have the size of a dice or the size of my thumbnail. That's how large a black hole would be. Okay, so this is the next, or almost the next pause. So one story that I want to tell you, and I will take a few minutes for that, is how we can actually build our very own black hole. And for that, we need to understand a little bit about the life of stars. So if you start once upon a time with a stellar cloud where you can form dense regions and protostars, then eventually those clouds can form stars like our sun. So if you have a star that isn't too massive, is like our sun, we will have a small star that in a few billion years may develop into what's called a red giant, planetary nebula, and then undergo or collapse into itself in what we call a white dwarf. Now, if we have a large star, so a star that weighs, say, 8 or 10 or 30 times as much as our sun, then it follows a very different path. So again, after a few billion years, it will, once the hydrogen and helium burning in their core stops, they will undergo a phase of expansion where they become a red supergiant and emit a lot of matter, fall back into itself, restart the burning process up to heavier elements. And again, once the heavy elements are all burned out, it will undergo an explosion. This time it's going to be a very violent event. It's going to be a supernova explosion. And the remnant, what is left over after that violent explosion, can become either a neutron star. So a neutron star is a very, very dense star that has only about 1 to 2 times the mass of our sun, but is compressed to about 10 kilometers or 6 miles. If our star originally was even more massive than that, then the final object will be the black hole that we talked about. So here we are talking about objects where, if we were to take our sun, then it wouldn't be larger than 1.8 miles, or say compressing our sun into the size, into a sphere that would cover just, the region between downtown Urbana and downtown Champaign. And in fact, you may have heard that the Nobel Prize for Physics this year was given for black holes, and one half of that Nobel Prize was awarded to Roger Penrose for the discovery that the formation of black holes, so what I just described, is actually a very robust prediction of Einstein's theory of general relativity. So that was the first part of the Nobel Prize this year, understanding that this kind of formation can actually happen. Okay, good. So now we have another short break for questions, and I see there are already a couple in the chat. Patrick, would you like to read them out loud for everyone?
I would love to read them out loud. So we have a pretty expert level question here. And this person asked, would you still get spaghettified if you got close to a primordial black hole that was very low mass?
That's a very good question. You would probably not really fall into those primordial black holes. So remember what I said about their size. So so if you take a primordial black hole that is very light, fractions of the mass of our sun, they would be extremely small, and their gravitational potential would be quite small as well. So don't worry about those. Yeah, unless of course you can shrink yourself to the size and then fall into this primordial black holes, then they may be quite deadly.
And we have another question coming in hot off the press. Will a neutron star stay a neutron star forever? Could it further collapse into a black hole, potentially if it formed with an accretion disk?
Yes, that may be possible, right? So if you have your neutron star and if you have an accretion disk such that you accrete more and more matter, and it goes beyond roughly 3 times the mass of our sun, then eventually it would collapse into a black hole. Another way of going, from neutron stars to black holes is if you were to take 2 of those and they were to collide. So they are then more massive than roughly 2 to 3 times the mass of our sun. We expect them also to form black holes. Okay.
Great. That's all we have for right now. So
okay, wonderful. I see.
Oh, hold on.
Yes.
One just came through right in the nick of time. Quick question about curvature. Could you have different regions of space with different curvatures? Or is it the same everywhere? And if so, why? No, it seems like we have another reconnection issue. And sadly, I am not a black hole expert, so I will refrain from answering or attempting to answer this question until our lovely speaker comes back. So again, in the meantime, if you need a new beer, feel free to get beer. And this commercial is brought to you by our friends at the McDonald Observatory in Fort Worth, Texas, who say, preserve dark skies. If you have an extra light on outside, turn it off. We want to look up and see the night sky. We want to see those stars. We want to do everything that we can so that our observations are as clear and as crisp as possible, and that cannot be done if we have these bright lights everywhere. So everybody, light pollution is bad, and yeah, just preserve those dark skies, turn those lights off, save some energy, save the earth, and yeah, thank you for that. So it's great, yeah. So please, send in questions while we have this bit of a break. It's great that we're seeing so many questions come in and all of this engagement, and hopefully our speaker can reconnect any moment now. And yeah, so if there is, I hope you all are enjoying your time with us this evening. Sorry for all of the connection issues. Can never trust Wi-Fi these days. And if you don't know, we have this AstroOnTap about once a month on these Thursday evenings at the same time and place. And so we would love for you to join us again, every month as this come on, because we'll keep doing this throughout this entire pandemic. So it looks like our speaker is back, and once she is set up, I'm happy to feed you more questions, or if you want to keep continuing with your talk and return to these at the end, we can do that as well. So it's up to you, Professor Witek. Do you have a preference for what you would like to do, because it's about 6:30, so about halfway.
Okay, yeah, which is perfect. I'm also about halfway. I would answer the last two questions that we had in the chat. So I hope you took this involuntary break by my internet provider to get a sip of beer. And I took the moment to actually draw a picture. So Chris, if you want to just swap a little bit again, and then I hope you can see what I drew here to answer Melanie's question. Okay, so let's try. Okay, so we probably saw a still picture for quite a while because I was following the YouTube stream as well. So Melanie asked about different regions of space and if they can have different curvature. So what I was drawing here is again the picture of our sun, and just as in this rubber sheet kind of picture, you know, if you were to describe the curvature of the sun like this, that would be one region of space. Our Earth is much less massive. So here the curvature would be much smaller, and you know, these would be different regions in space with different curvatures. Now, if we were to go from our sun some 26,000 light years away to the center of our galaxy, there we would find a black hole that has in its interior infinite curvature. So that would be at a different region in space with a different curvature. Okay, so I hope that answers your question. Then we have one question about the size of a black hole. So let's think about how massive a black hole can get. So the most massive black holes that we know about have about 10 billion times the mass of our sun. So if we remember in the beginning, I said our sun has about a radius of about 3 kilometers. So just by doing some simple math, we can estimate that the largest black holes that we know about have about 30 billion kilometers in radius. So that's the largest ones that we know about for sure. I will continue and I will take Malena's question in the end, which is an excellent question. So I will continue with the next question, which is how do we actually know that black holes exist? And one of the most striking evidences comes from our very own galaxy. So if you look at the Milky Way, then in the summer you should be able to see the constellation of Sagittarius. And within that constellation, Sagittarius, there's a very bright radio source that we have labeled Sagittarius A star. Now, what I will do now is show you an observation of that region around Sagittarius A star taken by the Keck Observatory, where they followed trajectories of stars around that center. So let me just play the video that you should see now. So in the center here, you see nothing, but you do see how stars evolve and how they move on trajectories around this object here. Now, by measuring these trajectories quite accurately, and by using our understanding of gravity, we can infer that this object here in the center that we cannot see is about 4.2 million times as massive as our sun. and it's compressed into a relatively small region of space. So the best explanation that we have for this dark object here is that it is a black hole. And in fact, that was the other half of the Nobel Prize this year that was given to Andrea Ghez and Reinhard Genzel for exactly that observation and that discovery, that at the center of our galaxy, we do have this supermassive black hole that weighs 4 million times the mass of our sun. But that is not the only observation that we have. Another picture that you may have seen, and that in fact colleagues of ours here at the University of Illinois have helped to take, is the following, which is this. So what you're seeing here is light deflected around another supermassive invisible object. So this object here is called M87 and has about 6 billion times the mass of our sun. We already knew about it because from that region there is a large jet ejected that we have observed before. But what we see here is an image taken in radio waves from radio telescopes across the globe, across the world, and then recombined the data to produce this image of what we call a shadow of a black hole. So we are not seeing the black hole itself, obviously, but we do see how light from an accretion disk around that black hole is deflected. And so if we were to have this black hole like this, and the accretion disk goes all around it, so part of the light that we see actually comes from behind our object. Yeah, because the light is deflected like you would have a lens provided by this mass. And that image was taken by the Event Horizon Telescope and published last year. Now, the last complementary observation that we have goes back to the chirp that we had in the very beginning. Remember, I was showing you this whoop kind of sound. Now here I have a computer animation of that very same event. So what did we hear there in the very beginning? Now for that, let's look at the animation where we are showing you, where I'm showing you here the curvature of space-time. Yeah, so and you see we have these very highly curved regions here that move around. That's where our black holes sit. So we have two black holes. Each of them has a mass of around 30 times the mass of our sun. They are orbiting around each other, distorting space as they get closer and closer and closer. And here we see a slow motion of how they actually merge into one single black hole, emitting a peak, a burst of energy in form of what we call gravitational waves. So these gravitational waves, as you will see in a moment, are really this kind of ripples and distortion of space. And then these waves travel towards us. Okay, let me stop that animation here. So that's another striking observational evidence that black holes exist. Since that first discovery in 2015, we have 10 more events of black holes, actually 10 confirmed events and 50 candidates that we will learn more about in the next few months, I hope, that tell us about the universe in a completely different way, because gravitational waves are in character completely different from, say, light or radio. Okay, great. So again, that was such a game changer, such a breakthrough discovery that Barry Barish, Gibson, and Ray Weiss were awarded the Nobel Prize in Physics in 2017 in lieu for an entire collaboration of 1,000 people that have made this discovery possible across the globe. Okay, so what's all that jazz about gravitational waves? What are they? How do we measure them? And what can we actually learn from them? Now let's start very slowly. What are these gravitational waves? Now we have already seen this picture or this animation of distortion and ripples in space-time. Now that may be a concept that at first may be a bit difficult to grasp. So let me take another analogy. And because I like water, I like go swimming, I like to play around in the water. So let me take another water analogy. Imagine you go swimming, go to one of the lakes in the summer, if you can go to the lakes again, and take a friend. And take your friend in the water and dance around, move around. What you will see are surface waves, but that's not what I'm interested in. I'm interested in the waves that you're producing underwater. So if you're kicking the water very, very hard, then you see that you can actually move the water and disturb the water itself underground. And that's how I would think of how gravitational waves disturb our space. Yeah. So in that analogy, our two compact objects like a black hole or even those neutron stars, if they are dancing around each other, they are disturbing space-time itself. And then these disturbances of space-time are traveling in the form of waves until we can detect them here on Earth. Now, that's all great. But to understand how we can actually measure those waves, let's try to understand what kind of effect they have. And for that, let's take the following picture. So let's take a ring of particles here. And let's assume that the gravitational wave moves through this ring of particles along this red line here. What it does now is the following. So we have our ring of particles. And as the gravitational wave travels through, it is stretching and contracting space such that your ring of particles will be stretched in one direction and get squeezed in the other direction. And then go back to its original position, and then it gets stretched in this direction and squeezed like so. And that's actually one of the effects that we are using to try and measure gravitational waves. But before we go there, let's try to understand how large these changes actually are, which is what makes measuring these waves so difficult. So the change in the distance, say going from this first ring of particles to the stretched version here, looks very large in this picture. But what we are actually trying to measure is the following, that this relative change, I have it as a formula here, but don't freak out. So this relative change, where we say the change in length over the size of our ring of particles, for example, is this incredibly small number, which is a 0 point, and then we have 21 zeros, and then we have a 1. Now, to bring that back to something that we can relate to a bit better, let's try to estimate, do some estimates. So if I wanted to measure, if I wanted to measure the change in a distance between Chicago, so close to here, to my hometown, which is close to Berlin, back in Germany, so some 4,400 miles away. So if I could measure that distance with the accuracy of the size of a proton, then that's what we are trying to measure in terms of, the change in length that we are trying to measure with gravitational waves. Or if we take another analogy, so the accuracy or the size, the change in length that we are trying to measure, if we were to try and measure this distance between our Earth or our Sun to our neighboring star, Proxima Centauri, which is about 4.2 light years away, then we would try to measure that distance as accurately as the size of the human hair. Yeah, and that's something that I find absolutely mind-blowing. And what I find even more mind-blowing is that we as scientists, as a scientific community, have actually managed to do that. So, and that's absolutely impressive. So how would we go about measuring that? And for that, we have built a number of instruments. The ones here in the US are called Laser Interferometer Gravitational Wave Observatory. And what are we trying to do? Well, we are trying to build a microphone that is really, really sensitive. And we make it really, really big because remember, we are trying to measure these extremely small changes in length. So the LIGO detectors are essentially a huge L-shaped interferometers where one of these arms has a length of 4 kilometers or, let me look that up, 2.5 miles. We have vacuum chambers to keep everything really, really quiet that are the second best human-made vacuum chambers after the LHC, the particle collider in Switzerland. And then we are trying to make our instrument very quiet by using really new materials for mirrors, by having a really dedicated suspension system. And the last thing that I would like to mention here, the first detectors that we had and that are here in the US are the Laser Interferometer Gravitational Wave Observatory, or LIGO, in Hanford, up in Washington State, and in Livingston in Louisiana. But these are not the only ones. So currently, well, they're currently all offline because of the pandemic and to undergo upgrades. But we do have another detector in Italy near Pisa, which is called Virgo. We have one called Kagra in Japan, in essentially in the Kamiokande mines. So if you have ever heard about the neutrino detector, Super Kamiokande, then that's essentially at the same site. We have a very small detector in Germany, close to my hometown, where a lot of the technology development is done. And then we hope to have another such ground-based detector in India by the mid-20s. So in some sense, we will have really a network of microphones that will listen to gravitational waves coming from colliding black holes or colliding neutron stars. But that again is not the end of the story. So we actually have really amazing plans for the future. So what kind of detectors do we think we will have in the future? Well, we already talked about those here on Earth, on ground, so these LIGO detectors. And we are planning to have even more sensitive detectors here on Earth by the 2030s. Then we are also planning for detectors in space. So there's, for example, the Laser Interferometer Space Antenna, or called LISA, for short LISA, where I'm actually involved in the development. And this will be a detector of 3 spacecrafts. shooting laser light in between them to try and measure their separation very accurately. If no wave goes through, those satellites will have a distance of 2.5 million kilometers, or roughly, so I'm not very good in the conversion to miles, so roughly 1.5 million miles, I would say. And with those space-based detectors, we would look for the collision of these supermassive black holes. So if two galaxies collide, eventually the supermassive black holes that have a few million to a few billion times the mass of our sun will collide, and then we can detect their gravitational waves using the space-based detector. Another source would actually be something like a supermassive black hole at the center of our galaxy, and a small object, a small star or small black hole orbiting around that supermassive black hole for a very, very long time. So that's something that we could hear with our space-based antenna. Now, and the last one, which is actually already ongoing, is what we call a pulsar timing array. So for that, I need to tell you that these neutron stars that we've seen in the very beginning, some of them are rotating rapidly. They are rotating within milliseconds around its own axis. And they are emitting radio pulse. So as they are orbiting around, or spinning around itself and emitting this radio pulse that we can measure here on Earth accurately. So these pulsars are the most accurate clocks in the universe, in fact. So we are measuring when these signals arrive here on Earth. And now, as is illustrated here, if a gravitational wave passes through space-time, then of course this radio pulse that comes from our pulsars may take a bit longer to arrive. So from the measurement of these arrival times, we can try to search for gravitational waves. And because of these large distances here, we are actually talking about waves coming from these billion to 10 billion solar mass black holes that are at the center of some galaxies. So in some sense, we are using the ground-based detectors like LIGO to learn about neutron stars and pulsars, and we can use pulsars, neutron stars themselves, to search for gravitational waves, which I think is quite impressive. Okay, so with that, I will come to my last slide and reconnect to what I said in the beginning, where I talked about the whispers of our universe. So what I mean by whispers is essentially these gravitational waves that tell us something unique about their origin, about their source. So what I would like to do to finish is just show you a few, or make you listen to a few gravitational wave signals, so signals that we modeled and then made into sound, so that you can listen to the orchestra of our universe. So let's start with a set of two neutron stars colliding. So let's see whether that still works. Okay, so these were two neutron stars. Now, remember I told you that black holes or neutron stars can be born out of these very energetic explosions called supernova explosions. Well, with a bit of luck, if it's close enough to us, we may actually hear this. And we make this a bit louder. So let me play that again. We will hear a plop. the extreme mass ratio. So remember, I was talking about a star or a black hole orbiting around one of these supermassive million solar mass black holes orbiting for a long time. Well, that's what we are after with the space-based gravitational wave detector, and that should hear something like this. There it fell into the supermassive black hole. And the very last one, the sound of our universe itself, which is actually a soundification animation done by Stas Babak, one of our colleagues in Europe. And that's what our universe itself would sound like, where we have a collection of all the gravitational wave signals coming from very, very large distances. So this would be essentially white noise, and then you will have a galaxy merger in there, which is coming up now, if you listen to it. There it was. So that would be a supermassive, two supermassive black holes colliding and giving up this chirp, the sound, on top of the noise that comes from the gravitational wave noise that comes from our universe itself. And with that, I would like to thank you for joining us today. I hope you enjoyed our journey. If you would like to learn more about black holes, about gravitational waves, and all that jazz, then I invite you to look at some of these links. So the first one is actually an exhibition, a poster exhibition that I developed with my colleagues back in Barcelona when I was a Marie-Curie Fellow there. And these are websites by some of our colleagues explaining and giving you a bit more details and providing some games if you want to learn more about black holes and gravitational waves. So thank you very much, and I will take a few more questions now.
Thank you, everybody, and thank you, Professor Witek, for that marvelous talk. I am out of beer, which means that our time has almost come to an end, but we still have our last section here, which is a section we like to call rapid fire questions. So we will get to all the questions in the chat that have not been answered yet, and please feel free to keep sending them in. Mm-hmm. And we'll start with our first question here, which was going back to an earlier part of the talk, where in the pathways of the black hole formation diagram, are there final evolutions of that diagram that become anything else? Or is the black hole neutron star at the end of the line?
So we already talked about the neutron star, right? Or say if you have, for example, two neutron stars that could collide to form a black hole. So you could extend that line there. For the black hole, at least to our knowledge, there's probably not coming much more after that. So of course you can take two of these black holes that form, oh actually this is interesting. So two of these black holes that form out of stars, and they, as we have heard, they can collide and form a more massive black hole. And that would actually give one pathway of how we might eventually be able to form these very massive black holes. So what I haven't told you yet is that it's still a big question mark of how we get these million to billion solar mass black holes at the center of galaxies. So, you know, there is more to come, probably through merger of black holes.
Great. Mm-hmm. Another question that we have is kind of simple one, and is it possible for planets to form around black holes?
That's an excellent question. So I don't know a mechanism how you would form planets around a black hole, but here, let me draw or put this question back. What do you think would happen to us if we were to replace the sun by a black hole? So we would have a black hole surrounded by certain planets. I'll think about it a little bit. In terms of gravity, not much would change. So if we were to replace our sun by a black hole of the same mass, the gravitational attraction that we would feel would be exactly the same. What would be missing, of course, would be the sunlight. So forming life on Earth would be more difficult, but in terms of gravity, nothing much would change.
Wow, that's definitely something that's going to keep me up at night. Our next question here is, what does the asymmetry in the picture of the black hole tell us? Is it asymmetric because of the orientation of the accretion disk or something else?
I'm not sure what you're referring to in asymmetry.
Yes, the asymmetry in terms of, I guess, the orientation of the accretion.
Yeah, so that's about the picture of the shadow around the black hole. So that tells us something about the spin. So because if your black hole is spinning, then the deflection of light is not the same from every direction. And that's how you can get this kind of asymmetry.
Another one for you here. How would the gravitational waves created by two black holes converging affect the mass near, affect other masses near those black holes?
That's a good question. So actually, let me see. Well, so the gravitational waves themselves, of course, are this distortion of space-time. So that's something that you would that's how masses would be affected, and that's in fact what we are using here, right? So how do gravitational waves affect masses or the shape of masses here on Earth? Yeah. Okay.
Right. And we have a pretty fundamental, question coming in. Something that I think about a lot is, did the Big Bang make gravitational waves?
That's an excellent question. We don't know because we cannot. Well, we hope that we can actually, learn something about the very early universe. Not quite until the Big Bang, but early using our space mission, using our LISA mission. So at the moment, we don't know. It's a big question mark.
Great. And as a bit of a follow-up, is there anything about gravitational waves that are different than what Einstein predicted, or is there something that's unexplained by general relativity?
There has nothing showed up yet. So gravitational waves, as we have measured them, are consistent with the predictions that we have from general relativity. That said, there's a caveat that I haven't told you about. So in order to measure these gravitational waves, we have to compare our data that we get. So the data that we get is essentially noise. And then we have to compare that against theoretical predictions of what we think this gravitational wave would sound like. And the predictions that we have at the moment were computed using Einstein's theory of gravity. So one of the project lines that I am working on is precisely questioning that and trying to understand how we can test Einstein's theory of gravity using gravitational waves. So what I'm doing there is try to make this prediction of how a gravitational wave would look like if we go beyond Einstein's theory of gravity. And then we will see.
Right. We have just a few more questions left, and if you still have questions, please send them in, and we're on our last couple here. the next one is, if the Large Hadron Collider, or LHC, succeeds in making black holes, what makes them safe? Why won't they consume and eat the Earth?
Oh my God, yeah. So that was a drama that was going on a few years ago. So 2 points on that. So first of all, if we were able to form black holes at the LHC, at the Large Hadron Collider, then they would be extremely small in mass. And in fact, they would be so small that quantum effects may become important. And these black holes would evaporate through thermal radiation, through what we call Hawking radiation. So this radiation is not relevant for astrophysical black holes that I talked about, but these very small ones would evaporate due to Hawking radiation. That said, so far there has been absolutely no evidence in the data by the Large Hadron Collider that any of these black holes have formed.
Okay. And if there was an event that created gravitational waves, how long would it take for them to reach Earth?
Okay, so that depends very much on where they have been created. So these gravitational waves travel at the speed of light. So they travel with 300,000 kilometers per second, or 185,000 miles per second. So for example, if we take this very first gravitational wave event that I showed you and that we listened to in the very beginning, that happened about so the distance was about 1.4 billion light years. So since it was traveling at the speed of light, it took it about 1.4 billion years to reach Earth.
Great. Wow. And our next question comes from Mr. Alex Galliano, who asks, how massive does the star have to be for its supernova to emit gravitational waves?
Ah, that's a very good one. So these supernovas that we hope supernova explosions that we hope we may be able to hear at some point in the future would be around, so originally around, say, some 20 times the mass of the sun. So, and that's where these type of supernova, we call them core collapse supernova. So these would be very massive stars that would end up being a neutron star or a black hole.
Great. Our next question is, what are the main outstanding questions that you are hoping to answer throughout your career? Very excellent question.
That's an excellent question. So I've been excited about black holes, I think, since I was a teenager and came across Stephen Hawking's book. So that's where all the excitement started, and that's actually what in part made me study physics. And I guess for me, it was always going towards trying to understand how the universe works, where do we come from? And at the moment, I think I would say I have like 3 main lines that I'm interested in. So one is to actually understand how gravitational waves are produced and how we can measure them within Einstein's theory of gravity. And as I think I mentioned, I am part of this collaboration to develop the laser interferometer space antenna, so this space-based observatory that I showed to you. One question is Einstein's theory of gravity actually, the correct theory of gravity? We know that there are still questions, or big question marks on how we can combine gravity and quantum physics. So, well, I'm not developing a theory of quantum gravity, but I do take the models that my colleagues and my friends develop and try to make a connection to these gravitational wave observations to learn something about what the theory of quantum gravity could be. And then another one makes actually a connection to the last speaker. So I can use my black holes to try and understand more about dark matter. So a certain type of dark matter candidates actually have a very interesting interplay with black holes that I may be able to tell you about some other time in more detail. So I'm using black holes to understand and learn more about dark matter.
Fantastic. And just as time is a bit running long here, so we're going to take these last two questions and then finish. And so our next question is, do you think white holes exist, and what observational signatures might they leave?
Oh, that's an excellent question, and I actually don't know. So,
all right. And then our last question of today is, what do you expect that the near-term major discoveries in this field might be?
So that's an excellent question and can be extremely broad. So again, one story that I haven't told you about very much are these neutron stars. And actually, when these neutron stars collide with each other, they give us insight into nuclear physics, into the matter that they are made of under extreme conditions that we cannot reproduce here in the lab. So I would expect major discovery there.
Dr. Witek, are you there? Seems like we lost her just at the last moment. And in the meantime, I guess we'll wait for her to reconnect to finish answering that last question. But in the meantime, if you haven't, please make sure to, if you can read my handwriting, like the Astronomy on Tap Champaign-Urbana page on Facebook, follow Illini_Astro on Instagram, subscribe to the AstroOnTap CU on YouTube, and because you're already on this video, you can just subscribe right at the bottom there and give this video a like, so that helps the YouTube algorithm. And then please make sure to follow AstroOnTap CU on Twitter. There's no TikTok for this page as well, or at this moment, but you know, if there's enough demand, maybe we can do that as well. But yeah, thank you everybody for joining. If you would like to just stick around for that one last question, that'd be great. And if not, we will hopefully see you next time. And you know, thank you very much for joining, for all your wonderful questions. I don't think we've had this many questions before for any of our Astro on Taps and our web broadcasting series. So thank you very much for that. And yeah, hope y'all have a safe and pleasant evening. Keep thinking about astronomy and gravitational waves, and yeah, make sure again to preserve dark sky. So if you have any extra lights, turn those off. Do the astronomers a favor. But yeah, great. Oh, perfect. We have Dr. Witek who's returned for our last question here, and just maybe to remind you what that was, because you got cut off. It was more of, what do you expect that the near-term major discoveries in your field might be?
Yeah. Okay, so thanks for your patience. Yes, neutron stars and their connection to nuclear physics. I think gravitational wave astronomy and black hole population, making the connection from our stellar mass black holes to supermassive black holes. Trying to understand dark matter, I think that's one of the long-standing questions we also have in modern physics, and then on a theoretical level, trying to understand what quantum gravity is, and that's probably more on a 50-year time scale than the next 10 years. But I think these would all be excellent questions. So with that, let me also thank our organizers. So Patrick, Chris, and Kale for hosting me. I think you did a fantastic job, and enjoyed talking to you and to all of you out there this evening.
Great. And with that, this concludes AstroOnTap number 7. Thank you very much, everybody, and we will see you next time.
Okay. Thank you.